All right, so okay. Hello everyone, I'm George, and this video is an introduction and overview of the DynamicalSystems.jl library. Now on purpose, this video will be quite short, and it is really targeting people that have already some kind of familiarity with nonlinear dynamics and would like to get started with the DynamicalSystems.jl library. Now there is also a much longer video that is targeting people that may not have already a familiarity with nonlinear dynamics. I will link this in the video description. So this will give you, let's say, a 10 to 15 minutes course on how to use DynamicalSystems.jl. But of course, before doing that, let's simply ask and answer what is this software library. And it is a general purpose software library for dynamical systems, nonlinear dynamics, and nonlinear time series analysis. And it contains several hundred algorithms of the nonlinear dynamics field. It is agnostic of the dynamical system at hand, which means that it doesn't matter if you have a discrete or continuous time system. It also doesn't matter whether it is low dimensional or high dimensional. Everything just works. And it is easy to use, intuitive, and easy to extend. Now, the point here is that this library is written exclusively and entirely in the Julia programming language, and it is very, very, very fast. That's pretty important. And now the reason I call this a library is because I really mean it in the literal sense. So it is a place where people go and learn something. And the reason I say this is because, well, of course, the library is open source, but we have also put a lot of effort to make the source code as transparent as possible and as easy to understand for someone as possible. But also, all algorithms implemented provide a high-level scientific description of what they do, and then furthermore also provide references to scientific papers that you can learn more about the methods or other methods. Now, this sounds fine, and let's say the ultimate goal for this library is to make the field of nonlinear dynamics accessible and reproducible. Accessible because some implementations that you might read about in some papers, well, you can actually use them immediately with this library. And reproducible because it allows you to write short scripts that make a lot of work about nonlinear dynamics, and this makes it easy to share and easy to also extend. And maybe when a new algorithm comes out, you can put it in this library. Okay, so this is, wait, I have to hide my face. Give me 1 second. Yep, all right. So this is pretty much the map of dynamical systems. This is everything this library has at this point in time. Of course, new things are added pretty much every month. And it has a lot of stuff. But the important point, and in fact the point of today's video, is that everything you need to know to use this library is just two things. This nice core over here that I illustrate. And then after you know the core, you can do a bunch of stuff. You can do delay coordinate embeddings, you can calculate entropies, probabilities, do a recurrence quantification analysis. Here is some advanced functionality for making your own algorithms for nonlinear dynamics. And this chaos tools over here, well, this is just a generic term to say this is a bunch of atomic functions. So these are functions that just work by themselves. You can take them off the shelf and do a bunch of stuff with them. There are really a lot of stuff over here, and I will not be going through this stuff, right? The reason there is this online documentation is so that you can just go there and see all this stuff instead. So now I will just put my face back on and go here, and we start immediately to, let's say, learn this core. So in this very nice short Jupyter notebook, we will see the two core data structures for dynamical systems. Of course, I will upload this notebook. You can find it in the video description. Now, there are two core data structures. One is called dynamical system, which represents a dynamical system, not surprises there. And the other is called a dataset, which represents a collection of points in the state space. In this tutorial, I will be creating two dynamical systems. The first is a discrete system. It's the Henon map that has these equations. And the second is the Lorentz system that is continuous time and has these equations over here. And there are some parameters that we will be using by default that the details does not matter. Okay. And let's start with a discrete dynamical system. Now, how to create a dynamical system is discussed in detail in the documentation string of dynamical system. So we just go to this documentation string and see what we can learn. So this is the documentation string. This is actually the online documentation of the dynamical systems library. Here is the link is over here. And now the constructor we need is this discrete dynamical system. And we only care about the first three arguments. Everything else is optional and we will not be discussing it here. So the three arguments is f, state, and p. F is a Julia function that let's say contains the evolution rule or the dynamical rule for this dynamical system. Our state is just some initial condition that does not matter very much. And p is a parameter container. And that's pretty much it. You just need these three things. Now, what is important here is what is the format of this function f. And there are two versions or two formats. The first version is called inplace, and it targets dynamical systems that are high dimensional. And when I mean high, I mean really high, like much higher than 10 dynamic variables. The second format is called out of place, and it targets systems that is low dimensional, so 10 or less dynamic variables. Okay, the out of place format is as follows. F is a function that takes as an input three arguments. The first is the state of the dynamical system, the second is the parameter container, and the third is time, and it returns a static vector that contains either the new state for discrete dynamical systems or it contains the rate of change for continuous time systems. The state of the system, therefore, is a static vector, and it is also the thing that the function returns. Static vectors are just vectors whose size is statically known at compile time. If you want to read more about them, you can, but you don't have to. Now, the second format, that is called inplace, is an inplace format, which means that besides the three arguments that we have already discussed, the function now takes a fourth argument as its first argument and modifies this argument in place. So it writes the new state or the new rate of change in place into x new. And in this scenario, both the state of the system but also x new are a standard Julia vector. Now these are mutable containers. Vector is mutable, but static vector is immutable. So all of this was a lot of abstract talk for something that is extremely simple in practice, and it's only like 5 lines of code. Let's do this. So we load the dynamical systems library. That's what this command does. And now we create the rule for the Henon system. So I create a function. The function takes as an input 3 arguments. The third argument is time, or here the discrete time. We don't use it, but we still have to make it part of the function call signature. And over here, I simply define the state and the parameters. Then I write the actual rules of the Henon map. This is exactly what I write here. And then I return a static vector that has the next state. I evaluate this, and then I create an initial parameter container and an initial state container. I evaluate this, and then I pass these three things into the discrete dynamical system container, and I evaluate this as well. Now this thing over here is the instance of a dynamical system. It contains all information necessary and can be passed to many of the 100 functions of the library. Let me correct this because this is not DS, it's Henon. All right. Now the best place to start on how to use this instance, this Henon thingy, is to use the trajectory function. Now, I forgot to say this. Notice that this is the output that Julia shows when you create a dynamical system. So it has some nice, neat information. It tells you what is the dimensionality, whether it's discrete, whether it is in place or not, and some other stuff. All right. Now, the trajectory function is actually quite straightforward. You simply give the trajectory to the dynamical system and how much time to evolve it for. And of course, there are many other arguments like what's the initial condition to start with, whether to have some transient time of evolution before that. There are a lot of stuff, but as we said, this is a really basic introduction. Okay, so we have run the trajectory function for 100 steps, and this is the output. It says here it's a two-dimensional dataset. Okay, the dataset is the second core data structure of DynamicalSystems.jl, and it is a container of equally sized points, specifically static vectors, and it has some, let's say, good indexing functionality. So first of all, as you can see, this is printed like a matrix that has two columns, and each column is the time series of each of the system variables. Now, when you access this kind of data set with two indices, it really behaves as the matrix it is printed at. But in reality, and when you access it with one index, it behaves like a vector of vectors. And this is actually what it is internally. Now let's see, if I access it with one index, the integer, it just gives me the second point, which is exactly this point over here. If I access it with one range, it gives me, well, the range of points from 2 to 5th time point. Of course, I can also access it with a range and then an integer, and this would give me this range, but now for only one of the two variables, specifically the second one. I can also normally iterate over this data set, and once you iterate over it, you iterate over its contained points. So here I loop over its points and I say, well, that's the point. And there is also the convenience function called columns, which simply decomposes the dataset into its individual time series. So that's pretty much the two structures. I will create one more dynamical system now for the Lorentz 96 system. And here on purpose, I will use the inplace format so that you see how this is done as well. So let me go back here to remind you the dynamic rule. This is the dynamic rule of the Lorentz system. As you can see, it has a lot of variables. You can choose how many variables it has. And I here is simply the variable index, right? Please don't confuse it with n here, which is the time index. Here I is the variable index because you have a continuous time system. So in any case, this is the rules of the system. So I go back down here and I start a function. And as I said in the beginning, this function has 4 arguments. The last 3 are the state, the parameter, and the time. And then you have this extra one, which is, in our case, the rate of change, because it's a continuous system. But we will operate in place in this rate of change, because this is now a mutable vector, or it will be once we create this in place form. So the function starts as before. Now I create here the equations for the Lorentz system, and you see, this is what I mean. I operate on this du vector in place. That's exactly what's going on here and here as well. And at the end of the function, I return nothing because this function does not have to return something. It simply operates in place. Now I continue similarly as before. I create an initial condition over here that has 5 variables. I create an initial parameter container, and then I instantiate the dynamical system. But now, of course, I'm using the continuous dynamical system constructor. And pretty much we are done. And of course, I can also get a trajectory out of this system exactly the same way as I did with the Henon system. So one more thing before I do some closing remarks. Continuous dynamical systems are evolved using DifferentialEquations.jl, which is a very, very high quality Julia library. And this means that any function that you use from DynamicalSystems.jl that takes as an input a continuous dynamical system, well, you can tune the solver properties to your heart's content using any of the ODE solvers and any of the common solver options. So these are some links you can follow. For example, I'm using here the ordinary diffec package because it is the one that provides ordinary differential equation solvers, as one you would expect. And here I make some nice arguments. I say, okay, the algorithm I want to solve my system with, I want to choose the Vernier 9, and I also want higher tolerances. I want absolute and relative tolerance that are The tolerances are low, not high. The precision is high. So I create this, and then I say, okay, now I will call once again the trajectory function, and I give it the same arguments. But now I will expand these nice keywords I have into this function, so that the function will internally now use the Vern9 solver and these tolerances. And this will just work. It will take a bit of time to compile, but it will finish compiling soon enough. And we will see the output. Okay, it's already compiled. So this now is the trajectory output using a much higher precision solver. And truth be told, that's kind of the end of the story here. Once you have understood how these two core structures work, the dataset and the dynamical system structure, well, using the rest of the library is straightforward. You simply have a look at the documentation string of the function you want to use, and then you are good to go. For example, you have a dynamical system instance. Let's say one of the things you could do is calculate the Lyapunov exponents of a given initial condition. Well, as I said, you just go to the documentation string of the Lyapunov spectrum, which is the function that calculates the Lyapunov exponents, and it tells you, okay, this function takes as an input a dynamical system, a second input n, and then some optional stuff that we don't care about at the moment. And it says that you calculate the Lyapunov exponents by applying a QR decomposition on the parallelepiped matrix n times. So for people already familiar with nonlinear dynamics, this involves the tangent space and decomposes it and rescales it n times. And there are a lot of keyword arguments here that you can have a look if you want to, but that's kind of it. It's rather straightforward. You simply call the Lyapunov spectrum function and you give it the Lorentz 96 instance. And this is the Lyapunov exponents. Now, this documentation string of the Lyapunov spectrum function highlights quite well why DynamicalSystems.jl is a library and not just a software. Because if you go down here, you see a description. Now, it says here, well, the method we employ is method H2 of this paper, as originally stated in the Benettin paper. And in short, the deviation vectors defining a d-dimensional parallelepiped in tangent space are evolved. Blah, 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 blah. And then if you click here, you go to the end, and it has some nice references of what's going on. And in truth, this was not a, I didn't handpick this function. Every function has the same kind of description. This is another function that has some other description. Lyapunov exponent from data. It's another function that has another description. Every function has a description. This is kind of a rule for merging functions into the library. So, anyways, you can do this. Another example of things you could do with a dynamical system is to calculate the Poincare surface of section or to obtain the fixed points of their stability. As an example, this is what I do here. I create an interval box, and inside this interval box, I find all the fixed points of the Henon map and their stability, and then I just print them. Oops, sorry about that. Yeah, I could be using interval root finding here, but no worries about this part. And then the other core structure is the dataset. And once you have a dataset, you could be doing many things with it. Now notice that the dataset is not only derived from the temporal evolution of a dynamical system and the trajectory function. You could be getting a dataset by loading in some experimentally measured data, or for example via delay coordinates embedding of an existing time series. For example, here I take the first time series of the trajectory of the Lorentz system. I automatically estimate an optimal delay time, and then I embed it into a 5-dimensional space. And then from this data set, I can, for example, calculate its entropy based on a given definition of probabilities. Here I'm using some kind of kernel density to get the probabilities. Or you can automatically estimate the fractal dimension. Here I'm using the Grasberger-Procaccia definition of the fractal dimension. It does a lot of automatic stuff, so this is something that should not be trusted. It is really just let's say a quick and dirty way to get a fractal dimension. Or you could get a recurrence matrix of a dataset, which is printed using Unicode. Actually, it's pretty nice. And from a recurrence matrix, you could get the recurrence quantification analysis quantifiers. And that's it. Now, the only thing that remains once you have understood the core data structures, which is dynamical system and dataset, is to just go to the contents page of the documentation, have a look and find and see if there is something that you need here, or if not, perhaps even consider contributing. So yeah, that's the end of this short video, and I hope it's a good introduction for people that know nonlinear dynamics but do not know the DynamicalSystems.jl library. So thanks a lot, and yeah, please do consider using it. And if you have a new paper that you want to publish that uses some kind of new algorithm, please consider contributing this new algorithm directly into the Dynamical Systems library, so we don't have to do it after you publish your paper. That would be pretty awesome. And yeah, thanks. See you. Bye.